Good afternoon. My name is Jesus Zambrano. I am a postdoc fellow at New Mexico State University down in Las Cruces, New Mexico. Today I will be talking with you about developing a time-resolved acoustofluidic flow cytometer for future FRET and fluorescent protein development studies. So if I get started here, briefly going to go through what flow cytometry is, the inherent issues we encounter with this platform, the evolution in our lab into a time-resolved platform, and of course, incorporation of microfluidics and acoustofluidics to bring together what we have today as an acoustofluidic flow cytometer. So briefly, what is flow cytometry? So flow cytometry is an apparatus. So flow cytometry is an apparatus that is able to count cells and extract the biophysical and biochemical attributes using fluorescence light and scatter light. Fluorescence light is measured in arbitrary units to measure the brightness of a given fluorochrome, whether it's exogenous or endogenous to the cell. Scatter light, so I have two types. One is forward scatter, one that is roughly proportional to the size of the cell, and then side scatter, which is roughly proportional to the granularity of the cell or what's the inner composition of that cell. Now, when I refer to fluorescence being measured in arbitrary units, this is actually where one of the issues that we see arises from, and that's spectral overlap. So if I have a 7-color system and I apply 7 bandpass filters, draw your attention to fluor's 488's bandpass region, you see that Pacific blue and phycoerythrin are intruding on that. And one way that cytometrists alleviate these issues through color compensation, which is basically a set of complicated math equations to mainly only just see the emission profile of fluor 488. So think of it as a coin jar where you just want to extract the quarters. In this case, if you want just the quarters in that jar, you're just going to have to take out all the pennies, the dimes, the nickels in order to just have quarters in that jar. And that's where the platform that we've developed in our lab comes in. So this is time-resolved flow cytometry, and it is able to extract the fluorescence lifetime parameter from any given sample. So this parameter is absolute, measured in nanoseconds that can be measured from 1 to 20 nanoseconds, and it is very sensitive to subtle changes within the cell's microenvironment. So there's the change in morphology, pH, and viscosity that will be detected by the changes in fluorescence lifetimes. And this is what we use to overcome the issue with the spectral overlap. So referring back to 2 slides ago when we were talking about the spectral overlap issue, instead of using emission profiles, now we're using absolute values, fluorescence lifetime values. So if you are inclined to just use one detector, that is actually possible with the system because each chromophore has its own unique fluorescence lifetime value. Now, like FLIM, our systems operate in time domain and the frequency domain. In the time domain, our excitation source, the excitation source pulses a light at your cell and excites any of the cells, whether exogenously or endogenously, and detectors measure that fluorescence decay over a period of time. You deconvolute that signal to acquire your fluorescence lifetime, and then convolute it again if you want to do further analysis on that. In our library, we focus on frequency domain, where you are able to measure the phase fluorescence lifetime and the demodulation lifetime. So how this is done is you modulate your excitation source. The modulated light excites your cell. The cell emits the fluorescence in a modulated state. And if I draw your attention to the figure down here, you can see that the fluorescence signal is demodulated and phase shifted with respect to the reference signal. From there, we are able to extract the phase shift value and then directly plug that into this equation and calculate our fluorescence lifetime value. We also have a demodulation lifetime value, but we will not touch on that for this presentation. So we have several applications of time-resolved cytometry, so in this case, we have used it in the past in protein conformational changes, fluorescent protein development studies, metabolic mapping studies, and eventually we want to move into fingerprinting or creating a comprehensive library of each chromophores fluorescence lifetime value. And that would be rather beneficial for many cytometrists and microscopists alike, and spectroscopists alike as well. So I alluded to that we used this in a past FRET study, and we were looking at the conformational changes of integrins in histiocytic lymphoma and we measured its response to an artificial stimuli, and it was able to do that quite well. So we saw subtle changes in the fluorescence lifetime value And we were actually able to transform this into the phasor space and create and visualize the conformational changes and significant heterogeneity seen amongst the cells, depicting their response. But of course, for us, this wasn't enough. We need better spatial temporal resolution for more advanced studies. And this is where time-resolved acoustofluidics cytometry comes in. Now, why microfluidics? Well, you think of microfluidics, you initially don't think increased throughput. I'll get to that a little bit later in the presentation. Reduce consumption. So you're using less of your sample, you're using less materials, therefore reducing your costs. Also, with using a smaller platform such as microfluidics, you aren't using as many complex optical detectors within its proximity. Therefore, you reduce the cost and complexity of the system. And most microfluidic devices are composed of polydimethylsiloxane polymers, which have increased biocompatibility compared to other materials out there. Now, the definition of microfluidics is the manipulation of fluids on a very small scale. So you're talking 10 to the negative 18 to 10 to the negative 9 liters. Usually the microcapillaries span no more than tens to hundreds of microns across in diameter. And usually most are composed of some sort of silicon-based borosilicate slides, though there are labs that have access to fabs, so they are able to perform photolithography in order to either dry etch or wet etch to create their own unique microfluidic devices. And it makes it possible to do even more complex things with this platform as well. And I briefly mentioned earlier that, okay, well, microfluidic devices, you don't necessarily equate that to increased throughput, but Steve Graves' group over at Benubio have been able to show this. So using parallel acoustic streams, you're able to bypass the linear velocity limit that is seen with conventional hydrodynamic focusing flow cytometers. And theoretically, you can achieve up to 500,000 cells per second using acoustofluidic focusing. Now, how this is done is that you take, so I'll use our chip as an example that was sourced from Benubio. We have our microcapillary is machined on an aluminum piece, and it is sandwiched between two borosilicate slides. Now, on the back side of this, you have a piezoceramic transducer. Now, this piezoceramic transducer is composed of composite material with perovskite crystals. As you apply a mechanical force to these crystals, creates this vibrational energy that is then reflected up towards the reflecting layer of our microfluidic device, and then sent back down to the matching layer, and just kind of oscillates in between and creates a standing acoustic wave. And in the middle of the standing acoustic wave is a pressure node. So as your cells come through this pressure node, depending on their density, of course, this is all relative to the cell's density. Usually general greater densities are going to align to the node where particles of lesser density, such as extracellular microvesicles, would align to the antinodes of this standing acoustic wave. And this complements what hydrodynamic focusing. So usually doesn't take hydrodynamic focusing out of the equation. And then we bring these three concepts into one system, and that's what I'm going to discuss now. So our system is composed again of aluminum and borosilicate. Capillary width is 500 microns. It also, again, the piezoceramic transducers on the back side of this microfluidic device, and it has a heatsink as well. We are driving that PZT at a constant attenuation of 1.5 megahertz. Now, we want to be able to evacuate the heat from that PZT. Otherwise, the heat stays there, and heat is allowed to rise. Heat continues to build in that PZT, reduces and degrades the performance of our PZT. The laser is the excitation source is introduced via a 20x objective lens, and the emission is collected via this objective lens as well. We initially started the system in a bright field setup. One of the inherent issues that we saw is that photodetectors were in the direct line of sight of the excitation source, so it was very difficult to overcome some of the laser background, though we still had other optics still performing very well. So instead, we migrated to an epifluorescence-like geometry where the photodetectors were out of the elimination path of the laser. and replace all of our objective lenses with higher numerical aperture lenses, included some extra spatial filtering, and that actually improved the image quality from our CMOS camera, and also improved. We were able to see some signal, fluorescent signal via the PMTs in the system as well. So that's the current setup that we have right now going on. The laser setup changed a little bit, and I'm going to show you that now. So initially, the OBIS laser, the 480 OBIS laser we have, was performing poorly in the near field. Gaussian profile was not uniform. So instead, we moved it to a far field where it had much better performance. So the laser travels about 1.5 meters before it reaches the first dichroic mirror end, and then is guided to the microfluidic device. The images are taken via the CMOS camera, and the emission, fluorescence emission, is back reflected to the backscatter and fluorescence PMT respectively. And then all this is amplified via a transimpedance amplifier and then visualized via our GUIs. Now, this is just showing the progression of the current system, bird's eye view, and of course, this is system in operation here. As we were testing and calibrating, especially in this case, I believe in this case, I was calibrating the fluorescence PMT. Now, there is a regime that you can create where you are acoustically trapping the particle within for prolonged interrogation. So you basically have actual forces that are canceling each other out, they're going against each other. And you can, like in this case, that's what I did here, and slowly allow the particle to transit through the excitation source. Now, if again in a regular scenario, your acoustic focusing is applied across the channel, you can have a linear, your sample traveling through the capillary in a linear fashion. Again, signal acquisition is a very, of course, major key component of the system. Initially, when we started getting fluorescence signal, very noisy signal, and that was because of some vertical misalignments that were still present within the system. Upon correcting those and then changing the time resolution to see the individual sinusoidal lobes, we're seeing a much cleaner signal, and that is depicted in this video here. You can see a very clean Gaussian envelope with our signal. There are some blips coming in here and there. That's due in part to some doublets coming in. That's okay. This is without acoustic focusing. We're still encountering some issues with the TRAFFC system, or that's what we've named it. So there's still no detected roll backscatter. We are working on some other alignment issues that may be causing this. We're also still fixing some of the data acquisition system issues, and we're still evaluating some like maybe a photo avalanche diode for potential use for future use in this system as well. Now, we want to finish calibrating the standardizing the system this summer and move on to the FRET and fluorescent protein development studies, even some COVID-related studies as well. Now, next year, our hope is to get acoustic cell sorting going so we can better facilitate our near-infrared protein development, and maybe move on to something more, evolve the system to something more comprehensive later on down the line. I want to extend a warm thank you to the Nubio, Steve Graves, Travis Woods, and Jim Fryer for loaning us a microfluidic chip of theirs. And of course, my research group, and especially a special thank you to my mentor, Dr. Jessica Houston. I will take any questions that you have. All right, thank you.